And maybe we'll get started. So hi everyone, thank you for coming. Today we have Nikolai Panery from UCL giving us a talk about his work on OPTIMET, which is an HPC code for modeling a nonlinear optical response for arbitrary clusters of nanoparticles. And this was part of his work on the eCSE project. So Nikolai, whenever you're ready, please take it away.
Yeah, thank you, Alexei, for inviting me to give a talk in this seminar, and also for your introduction. Yeah, so as it was mentioned, today I will present OPTIMET, which is an HPC code that describes computationally linear and nonlinear optical response of arbitrary clusters of nanoparticles, as it implemented on ARCHER2 and other HPC machines at the UCL. And here by arbitrary, we mean arbitrary shape, arbitrary distribution of particles, arbitrary material like dielectrics, metals, semiconductors. So essentially it's and also distribution of particles. So it's quite a general code, and provides the optical response both in the linear scattering and nonlinear scattering. Essentially, in nonlinear optics, by nonlinear we mean generation of new frequencies. So yeah, the code was developed as a part of eCSE project, and the main developer was Dr. Ivan Sekulic. So this is the outline of the talk. I will start by presenting the multiple scattering matrix, which is the core method that it's implemented in OPTIMET. And I will start with the linear regime. Linear regime is wave scattering, what we call fundamental frequency, so the incident wave. First, the MSM method for a single sphere. So this is can be treated analytically. So this is a standard Mie theory developed more than 100 years ago. And then the extension to multiple spheres. And here the whole treatment becomes more complicated. Then the extension of this MSM method to the nonlinear regime. So that means that regime that we generate new frequencies, and I will focus on second harmonic because this is the sort of probably most investigated nonlinear optical effect because of the applications. So here, second harmonic generation for a single sphere made of centrosymmetric material like metals, noble metals, gold, silver, important dielectrics in optics like glass, silicon, and polymers. This it's also treatable analytically, but the whole thing is quite complicated for a single sphere. But provides good testing for the code. Analytical methods are always good as a testing of the code. Then the extension to clusters of spheres, and finally the extension to non-spherical particles. And in the second part of the talk, I will present the code, OPTIMET 3D, we call it, the code structure and workflow, the parallelization strategy, adaptive cross approximation. This is a numerical technique used to further speed up the code, some numerical examples, and scaling and performance characteristics as implemented on ARCHER2. And in the end, I will present the main conclusions and some ideas for future work. So I will try to find the right balance between the science part, the physics part, the computational part, computer science, and the software development, because I was thinking that there might be people in audience from all these areas. So just a very brief background related to electromagnetic wave scattering. It seems that all letters in like Greek letters were transformed in Roman. So a general classification of photonic materials. We can use the relative size of wavelength. This L should be wavelength of the primary unit cell as wavelength of the incident wave as compared to the characteristic size of the structure A. So if the structure is periodic, as shown here, A is the period, and if the structure is disordered, like a cluster of nanoparticles, then is the characteristic distance between the particles. So when the wavelength is much smaller than the characteristic distance of the structure, we deal with the geometrical optics. So this is not particularly interesting from a computational point of view. It's just the rays optics. The second regime is the most challenging from computational point of view, when the wavelength is comparable to the distance between the particles and the size of the particles. So in that case, we deal with photonic crystals or plasmonic crystals when the structure is periodic, or particle clusters, optical clusters, when the distribution is random. And finally, when the wavelength is much larger than the characteristic length, the optical response is similar to that of homogeneous media, or more recently called metamaterials. So in this case, we can apply well-known methods like effective medium theory, and again, computation is not so important, not so critical. And based on that effective medium theory, technique, we can calculate effective properties like dielectric constant, effective dielectric constant, or effective susceptibilities, and so on. When dealing with electromagnetic scattering, there are actually quite a few challenges, and here I will just outline the main problems. So first, the electromagnetic field, as we all know, it's a mixture of interrelated two vector fields, the electric and magnetic field. And also the sources of these fields, like electric currents, polarization, and so on, are also vector fields. So essentially, we have to compute, we have to solve a problem, set of equations for vector fields. Then also in the regime that I said that it's most challenging, there are multiple spatial scales. So in the far field, the electromagnetic field depends in some way with in space, as compared to the near field, where it's much more inhomogeneous. And also we have the in-between regime, where actually there is not a very clear way to treat the field. So it's a multiple scale problem. Also, there are complex boundary conditions, because the boundary conditions for electric and magnetic field are different. They contain sources, which, as I said, are vectors. Then we have tangent, normal vectors, different boundary conditions. So this is not a trivial problem. Then the materials are frequency dependent. They are dispersive materials. As we all know, metals are quite dispersive at optical frequencies. And this has to be taken into account. Then these materials at optical frequencies can have, in some cases, strong nonlinearities. So we have to take into account the nonlinear optical response of the materials. And also, there are multiple wave scattering in such a structure, in the sense that the electromagnetic waves can scatter within, let's say, a cluster of particles, and this has to be taken into account. So this is a challenging problem, and as I said, one additional issue is when we add nonlinearity to the problem. So this is just an example of a nonlinear response, a nonlinear optical process. It's actually what we use in our code. So in general, a generic example, we have a light source which emit usually a laser, emit light, monochromatic light at frequency omega, and interacts with a nonlinear optical system, can be a nonlinear crystal or a distribution of particles. And as a result of this interaction, higher harmonics are generated, in this case, second harmonic. In a second harmonic process, two photons with frequency omega combine and generate a photon with frequency 2 omega. And then you analyze the spectral output of this process. You separate the frequencies omega and 2 omega. So from practical point of view, there are quite serious challenges because this nonlinear optical response in general can be weak. So people need to develop new methods to enhance nonlinear optical response. And this in this area, using metallic nanoparticles, it's one key approach. And our code, it's specially designed for such approach. And also from theoretical point of view, nonlinear optical processes are complicated because they are described by complicated mathematical equations. And these are sort of a very brief, so all the colors, it seems that are gone here. Sort of a very brief presentation of main numerical method in electromagnetism, essentially for solving Maxwell equations, computational electromagnetism. The two main classes are in the time domain, when we solve the time dependence of the electromagnetic field. And this is done by solving integral Maxwell equations or differential Maxwell equations in differential form. And there are many such methods like FDTD, finite integral method, and so on. And also in the frequency domain, when we find the optical response of a medium at particular frequencies. And our method is somewhere here, like it's an integral method. It's similar to method of moments. And also there are methods that incorporate like wave mechanics, charge particle motion, quantum mechanics, solving Schrödinger equation together with Maxwell equations, thermal effects. So it's quite a large field of complex numerical methods. So now let's consider the topic of what we did. Optical wave scattering from particles. And we start with really the simplest case, when we have a single sphere and at fundamental frequency. So there is no extra frequency generated in the system. We have a wave with frequency omega that is scattered by a sphere. And this is a well-known problem. It's there is an analytical solution, Mie theory. And essentially, we impose boundary condition on the sphere for the electromagnetic field, for the tangent electromagnetic field. And this leads to what is called transfer matrix associated to the sphere. So basically, we expand the electromagnetic field, the incident wave. So this is known. We expand it in vector spherical harmonics, M and N. These are a complete set of vector functions, and we use vector functions because the electromagnetic field is a vector field. So this sum actually, it's composed of two sums, because actually two sums, because we sum over the angular momentum number L and also the magnetic number M. So it's here it's sum over L and M. And the incident field is expanded, and these coefficients are known because the incident field is known. Then we expand the scattered field and the internal field inside the sphere, and impose boundary condition. The tangent field, electric field, and magnetic field should be continuous at the surface of the sphere. And we write it like this, in the sense that on the right-hand side we have the known fields, and on the left-hand side we have the unknown field. And using the boundary conditions, we can set up an equation that relates the incident field coefficients Q and P here with the scatter field, which we want to find, B and A. So this matrix, it's called the transfer matrix for a single sphere. If the scatterer is a sphere, this matrix is diagonal, and coefficients, the elements of the diagonal, can be found analytically. So this is a good problem, because we can test the code. We can use it as a benchmark problem. Then things start to become more complicated when we consider multiple spheres, again at fundamental frequency. So there are no nonlinear processes yet. So now we have to take into account the fact that a wave, before reaching, let's say, the point P here, can scatter many times within this cluster. So we have to take into account multiple scattering processes. Also, this is taken into account by considering the incoming field on some sphere, nth sphere, is the sum between the incident field that comes into the sphere directly from the incident beam, the field that comes to the sphere after undergoing many scatterings in the cluster. So this is written here. This is the field of the incident wave, and this comes from scattering from different particles. And there is, for some reason, this was messed up here. So essentially, the problem is that we expand the fields for each sphere in the coordinate system of the spheres, in these spherical harmonics. And then we have to bring all these fields into some common coordinate system, which is chosen usually at some point, sort of a center of mass of the cluster. And this is actually what these translation matrices do, bring the fields from all the spheres to some point. So now here we express the field in the coordinate system of the cluster. So again, using the boundary conditions as before, we end up with a very large matrix. So all these are known coefficients. They contain the coefficients of the incident field. These translation matrices that are known, beta, and these are transfer matrix for individual spheres. These are also known. So all this vector, which is a very large vector, is known, and these coefficients F contains scattering, the coefficients of the scattered field. It's exactly what we need. And this scattering matrix of the system, on the diagonal is the identity matrix, and then off diagonal are essentially biparticle interactions. So for instance, this is the interaction between particle 1 and particle n. So for a linear system, the most complicated, computationally, the most complicated part is to populate this scattering matrix. And then it's solved numerically. We find the field F, the vector F, which contains all scattering coefficients. So essentially, once we have these coefficients, we can solve the problem. They give us the near field anywhere near the spheres. And also they give us the far field behavior in the sense that we can calculate the scattering cross-section of particular spheres and also the scattering cross-section of the whole cluster. It's what essentially you want to calculate, because this is what you measure, someone measures in the far field. So this is the linear problem. Now, once we know the linear problem, as I said, we can find the field in the far field, but also the near field. And what is important for the near field is the near field on the surface of the particles and also inside. And this is clear if you want to calculate second harmonic. So nonlinear frequency generation, incoming wave has frequency omega, outgoing waves have frequency 2 omega. So the important point is that at second harmonic, there is no incident field. There is no laser at second harmonic. So second harmonic is generated by nonlinear dipoles, nonlinear sources on the sphere, described by this equation, and also nonlinear, actually nonlinear quadrupoles, electric quadrupoles and magnetic dipoles inside the sphere, described by this equation. So here, electric field, it's the electric field at fundamental frequency, which we already calculated. So at second harmonic now, we use as a source, not an incident wave, but this source is at the second harmonic. And this is valid for centrosymmetric media. So these are media for which the lattice of the optical medium has inversion symmetry, like for instance, a cubic lattice. And this is the case for most important media in nonlinear optics, like metals, noble metals used in plasmonics, silicon, glass, and so on. And this is why we focus on this nonlinear optical response. So again, we expand the field at fundamental frequency at the second harmonic in spherical harmonics, vector spherical harmonics. And now we use nonlinear boundary conditions. So the field is no longer continuous, the tangent components are no longer continuous, but they have discontinuities at the surface given by electric and magnetic currents. And these currents are determined by the nonlinear polarization. So the point is that these current sources are known at second harmonic because we calculated the electromagnetic field at fundamental frequency. So this polarization essentially is known. And again, for a single sphere, we can derive a matrix equation, which a transfer matrix that relates the coefficients associated to these sources, which are known, to the scattering coefficients in the far field A and B. So again, for a sphere, this matrix is known. Now the extra complexity step when we consider multiple spheres at second harmonic, and the whole treatment is similar with the fundamental frequency in the sense that at the second harmonic we have to consider multiple scattering processes. So the total field at the second harmonic now is the field radiated by the sources on each sphere that reaches some sphere. So the first field is field directly radiated by the sources on the sphere. And then there is an extra field, which is due to multiple scattering in the cluster. So that means that the field can reach a sphere directly from other spheres or after undergoes multiple scattering processes. And again, there is a transfer matrix at the translation matrix at second harmonic, which brings fields expanded in the coordinates of spheres to some common coordinate system. And again, we end up with a similar problem. This vector is known because it's related to sources, and sources at second harmonic, so can be calculated. And this vector f contains the scattering coefficients. Once we know f, vector f, we can calculate everything at second harmonic. And again, you can see that the scattering matrix at second harmonic, capital omega, has a similar structure. And again, for sphere, the computational load, it's mostly to calculate this scattering matrix. And this was developed in here in a recent paper. And the final complexity is when we make the particles spherical. This is obviously a case of practical interest, because usually, for instance, in colloidal solutions, or when you make such systems, they are not really spheres. So again, for fundamental frequency and the second harmonic, we have extended this formalist multiple scattering matrix, arbitrarily shaped particles. The key complexity in this case is that the T matrix for a particular object, if the object is not spherical, is no longer diagonal. So it's a full matrix, and the matrix elements are given by integrals over the surface of the object and volume of vector spherical harmonics. And for a sphere, these vector spherical harmonics are orthogonal, and that's why the T matrix is diagonal. And for arbitrary particles, actually, this is the key computational, the main computational load. When we calculate all these off-diagonal elements, these integrals, because we have to generate a mesh for each particle and then calculate these integrals over these meshes. So all the theory, and it's here on this archive paper. We submitted it recently to PhysRedB. It's in review. So now let me move to the sort of second part of the talk, the description of the code. OPTIMET, we call it OPTIMET 3D, from optical metamaterials and 3D. So this is an in-house developed electromagnetic software based on multiple scattering matrix method that I just presented. And also this method is called transfer matrix method. It's a fast, accurate, and parallel C++ scalable C++ code that was installed and tested on ARCHER and ARCHER2 and several other HPC machines at UCL. So the linear module solves the linear scattering problem at fundamental frequency, and the nonlinear module second harmonic, but can be easily extended to other processes like third harmonic generation, four-way mixing. That would not be difficult to sort of to expand the code to other nonlinear processes. We also use a matrix compression algorithm because this scattering matrix contains a lot of elements that are very, very small. That's due to the interaction of particles that are far apart, electromagnetic coupling between particles that are far apart. So this algorithm actually speeds up a lot the computation. We parallelize it through MPI, using MPI, and with a CMake, it's portable to some extent. And here is just a summary of some applications that can be used, like bulk 3D photonic metamaterials, radar antenna application, because we can calculate scattering from particles of arbitrary shape, to calculate nonlinear susceptibilities, just using effective medium calculations. This is some more exotic material, hyperbolic, zero index. For solar cells, for instance, if we use metallic particles, we can calculate the local field enhancement and see the efficiency enhancement. Optical linear and nonlinear tomography. And actually is not yet, because it doesn't handle periodic structures, so it's not really, it can calculate band structures, but for amorphous disordered systems. And this is the block structure of the code. So we start with parsing the input file, which contains simulation parameters like the type of incident wave, and we implemented the plane waves and the Laguerre-Gauss beams. The geometry, like the shape of different particles. The material type can be metal, can be dielectric, semiconductors, and a mixture of such materials. The only thing that matters is that the nanoparticle should be homogeneous. So it cannot handle, the whole method cannot handle materials which particles that are inhomogeneous. But in practice, you don't really deal with such cases. And also the output, what you want to calculate, like scattering cross sections, near field, far field. This is set up here. Then in the first step, it computes the scattering matrix at fundamental frequency S, and also the excitation vector, so the known incident field, the decomposition of the incident field. And this can be done serial or parallel, depending on how many particles are in the cluster. Then we solve this linear system to find the vector F, which contains the expansion coefficients of the field at fundamental frequency. Then this information is fed up into the nonlinear module. And if we want to calculate the nonlinear, if we don't want to calculate the nonlinear field, it just goes to the post-processing, like calculating near field, scattering, absorption coefficients, and all these are the linear response. And if we are interested in the nonlinear optical response, then we calculate the scattering matrix and the excitation vector at second harmonic. It's essentially the same process, but now for the second harmonic, we solve the linear system at second harmonic, and then again we can calculate the cross section and other quantities at the second harmonic. And these are the parallelization schemes that we use. Actually, there are two levels of parallelization. For spheres, the most effective way to parallelize the system is that this scattering matrix, it's calculated column-wise. So this is the first particle, this is the interaction between first and second particle, and so on. So the columns are fed to different processors in such a way that the workload is balanced, depending on how many processors are available. So this is the most convenient way to do it, efficient way to do it for a parallel, for a linear code, linear part. If we are interested in the nonlinear scattering, then what is parallelized is the calculation of each of these matrices. So because this is actually quite intensive computationally, so all these matrices, because the off-diagonal elements of these blocks contain surface integrals, so these blocks are sent to different processors, again in a balanced way. And all the matrix vector equations are solved by direct LU decomposition or iterative GEMRES. So this is actually faster. And both are implemented in Scalapack. And as I said, in this for these matrices, so if let's say particle 1 and particle n are far apart, then this block and this block will contain many elements that are close to zero, vanishingly zero elements, except on the diagonal. So then it's actually the computation can be sped up by using this adaptive cross approximation. So basically we replace these matrices with much smaller matrices using this standard numerical method. So basically, we reduce the total size of the matrix of the cluster, and the dimensions of this new matrices actually can be much smaller than the initial. Here also, it's these are messed up. And I will later on comment on how much this speeds up the code, but we observe that computationally it's cheaper than SVD decomposition, and it helps this. And this was part of the project, one of the tasks. So this algorithm, this compression algorithm, it's embedded both in the linear and nonlinear part of the code. So these details, I'm not. It seems that the lines that contain mathematical equations don't display properly. So this method is invoked, as I said, when we calculate the matrices at fundamental frequency and at second harmonic. So it's very easy to be blended with the existing code. And as I said, in the case of large clusters, and we consider clusters with thousands of particles, many of their interaction lead to matrices with very small elements. So this compression is quite efficient. And now let me sort of present a few examples, starting from very simple ones that you can solve analytically on a PC, to more complicated. So this is the field scattering from a gold sphere, and this is from a silicon sphere. You see that the electromagnetic field doesn't penetrate in a metal as expected, but it penetrates in a dielectric. And this is the scattering cross-section, both at the fundamental frequency and second harmonic, calculated with the code numerically, and also using an analytical. So especially for spheres, for dielectric spheres, there is a good agreement between analytical and numerical examples. So here we use just a very few spherical harmonics because it's kind of a toy problem. And then we use more serious examples. For instance, a cubic cluster of 345 particles, 7 by 7 by 7, of silicon spheres. This is the radius of the spheres, and the center-to-center distance, it's 100 nanometers. And for each sphere, we use 160 vector spherical harmonics. And this compression technique reduce the memory need by to more than 16%. So almost reduce the memory requirements 10 times as compared to the uncompressed matrices. And this is the field at fundamental frequency, and this is the field at second harmonic. An interesting thing here is that you see at fundamental frequency, the field penetrates through the structure, but it penetrates very little at second harmonic because the whole system has inversion symmetry. And as I discussed, in the case of system with inversion symmetry, the field inside the object, it's vanishingly small. And we see this when we make composite materials, like materials made of spheres, not at atomic level. So this is an interesting, relatively interesting effect. This is for a cubic cluster of gold spheres of 8 by 8 by 8. So just a comment, these are way beyond what a PC can do. So on a PC, using finite element method, you cannot go beyond maybe 2 or 3 particles. Whereas here there are hundreds, and as I said, we've been able when we tested the code scalability to go to thousands of particles. And this is the scattering cross-section with and without compression. So we see that it's actually good agreement. So there is no accuracy loss when we use compression. But as I said, we gain almost an order of magnitude in computational time and the memory. Again, these are the fields, and the light comes from below. So again, here you see these are gold particles. Electromagnetic field doesn't penetrate in a structure more than 1 or 2 rows of spheres, because they are metallic spheres. If you compare with dielectric spheres, what we see here, the electromagnetic field go through the whole structure. And this is another example with more particles. This is 10 by 10 by 10, so 1,000 particles. And we calculated the scattering cross-section at fundamental frequency and the second harmonic. Also on Kathleen, which is the HPC cluster at UCL. We observe more or less a similar behavior. Very little field penetrates beyond the third or so row. And in this case, this compression method led to about 20% of memory use as compared to uncompressed case. And now a simple case of non-spherical particle, spheroid, gold, again made of gold and silicon. So in this case, what we did, we considered the aspect ratio in such a way that it went closer and closer to a sphere, and we observed that the scattering cross-section, both at fundamental frequency and second harmonic, converges to that of a sphere. So at least this simple test shows that the code works. And a dimer, when we have two spheres, this is a fundamental frequency and second harmonic. The fields were expanded in 140 vector spherical harmonic. If we try to solve this, so basically only 140 are knowns. If we try to solve the same problem using finite element method, we will need like cover these structures with meshes. Then we would need about 67,000 unknowns to reach a similar sort of frequency dependence of the scattering cross section. And as I said, beyond 3 or 4 particles, this is essentially impossible. Whereas on using our method, we can go to thousands of particles. And this is an interesting, from sort of science point of view. Here we have a centrosymmetric material. So we see that at the fundamental frequency in the centrosymmetric material, most of the so this is fundamental frequency and this second harmonic. So most of the second harmonic is generated at the boundary of the cluster. It's exactly like in the case of a metallic particle, where most of the second harmonic is generated at the surface of the particle. In this case, this second harmonic is generated at the edge particles. So essentially, if we look at these spheres as being atoms, we see that the atoms at the surface of the cluster generate second harmonic, the same way as for metallic particles, the atoms at the edge, at the surface of the particle generate second harmonic. If we use a non-centrisymmetric distribution, we see that it's a completely different, the second harmonic is generated throughout the system. So what happens at atomic level, our code can replicate at sort of nanoscale in clusters of nanoparticles. And a few graphs related to the scaling of our code. So we consider the calculation of scattering matrices at fundamental frequency and second harmonic. So this is the top panel, and how it scales with the number of processes involved. And this is the speed up factor. And we consider the number of processes from 8 to 512. So we couldn't do actually a very extensive scaling calculations because the time that it's allocated to these processes, it's not actually a lot of time. So it's very good for code development and testing, but for this type of analysis, it's a bit restrictive. So then here is the scaling when we consider the compression method and without compression. And we see that again, there is a good scaling. And here we tested several, again, scaling with the number of processes when we consider fundamental frequency and the second harmonic. When we solve the whole system with different ways like GEMRES and direct inversion, and also the benefits of this compression method was not necessarily in the computational time as much in the memory that was used, because this compression technique, it's really to reduce the size of the matrices that we deal with. And yeah, the conclusions, we developed this scattering analysis for particle clusters, and we consider that this problem has important applications in metamaterials, atmospheric dust particles, nanoantenna, and we consider both spherical and more a case of more practical interest of non-spherical particles. We consider both linear and second harmonic calculations. And the description of OPTIMET, which was developed as part of this project, and we would like to acknowledge the financial support from this program, CSE. The code is fast and scalable. It's installed on Archer, so it's for everybody to use. It's parallelized using NPI, and both the calculations and the post-processing part stages are parallelized. We use this acceleration tool to reduce the matrices that we deal with, and therefore the memory requirement. And the code is freely available at GitHub here, and as I said, also it's installed on Archer 2. So I will stop here, not before thanking you for your attention.
Okay, great. Thank you, Nikolai. Are there any questions? Just feel free to speak up, I think. Okay, so David has a question. You mentioned that you had some issues measuring scalability on slide 25.
Yes, so what I mentioned is not measuring the scalability. So this is an CSE project, and it comes with a particular amount of time, computational time that it's allocated. And in order, we just seen that this time is not really enough to try to scale this, let's say, for a very large number of processes or number of particles, because the computational time that we've been allocated would be consume quite fast. So there are no scaling issue from a computational point of view. It's just the allocated time. And actually, we requested, we asked for a bit more, for some more time when we work on the project.
Just as a follow-up to this, I guess, what sort of scales would you like to be able to run at for, I guess, scientific purposes?
So I see that actually our code now can handle the largest number of particles compared to other, to what is on sort of I've seen. And it's definitely the only code that handles nonlinear optical response. So most of what exists, it's a linear response. And as I said, if you consider like 1,000 or even in the linear case, we could go to 10,000 of particles. That's enough to study quite interesting effects. As I say, you can study composite materials because 10,000 particles, it's already enough to construct a medium which has effective medium properties. You can study, for instance, interesting physics phenomena like Anderson localization. You can distribute the particles and size of particles randomly, and you can look at light localization, and our code can provide this functionality. You can look at light Anderson localization, for instance, both at fundamental frequency and second harmonic. So in some sense, it can be that light is localized at fundamental frequency in certain regions. The second harmonic is generated in those regions because that's where the nonlinear sources are. But then as it scatters in the cluster, gets localized in different regions because it has a different wavelength, second harmonic. So the localization, sort of those localized Anderson modes will be in a different places. So you can actually study, I think, quite interesting effects when you look at light localization at different frequencies in the same structure in different places. So I see that the code now has the functionality that would allow someone to essentially to study really state-of-the-art physics.
Okay, that's great. Thank you. Any other questions?
And as I said, it's available.
Okay, so another question. Do you have scalability graphs on other platforms?
We have something on Kotlin, which is the HPC platform at UCL, but would cover essentially this region. So we cannot go for more than 100. It's difficult on Kotlin to get computer time in the sense that your code will just not start because it's if you request more than 100 or so, maybe 200 processors, it stays forever in the queue. So that's why I didn't present anything. It was very good for testing, like small number of particles to see that the code works, because we develop it both on Kotlin and ARCHER2. But for this type of scaling, we could, I mean, the data is really relevant. We don't have quite relevant data on Kotlin. And these are the only two systems that we had access to.
Okay, great. Thank you. Okay, any further questions? Okay, if not, then I think it just remains to thank Nikolai again. So thank you for offering to do this presentation. Yeah.
Thank you.
Thanks.
Okay, bye.
Bye.